So I sort of forgot and then recently realized when I was looking at the website, I still haven't been able to come to any of the recitations.
Ask me in class. I want to talk about the recitation
Okay.
in 2 minutes. Many people care about it.
Have they still been just doing Python review?
No. I'll talk about it. Yeah. Okay, so let's start. Can you hear me at the back? Okay, so it's been a long time. Many things happened between last time and this time. Some good, some not so good. So let's see. So homework 1, there's a smiley face there. So almost all of you are done. So in fact, the real deadline, if people want to use all the Slack time, which I suppose some of you are, is tonight. But I'm assuming all of you were done. And I want to say something about it. So I would say that about 2/3 of you, it seems like, didn't have real problems. You know, it's good that you have some problems. It's a problem set, after all. And about 1/3 of you had more significant problems. I think that some of the people that had more significant problems are not here, and maybe that's why, but I don't know. But basically, I want to say something about my philosophy that you probably got already. So I don't think about the problem sets as something that is going to be very easy. You basically give us back what you've seen in lectures, but rather it's supposed to complement the lectures and give you stuff that it's actually not so easy to do in lectures, and the right way to do it is by playing with data, playing with algorithms, struggling a little bit, trying to figure out what is that I really want to do. So after all, this is an applied machine learning class, and the idea is to try a little bit to challenge you with problems that you may encounter next year, 2 years, when you actually get data and a problem that is not completely well defined, but you nevertheless have to solve it. So we are going to try to do a better job defining the problem as much as possible, but still give you a few things that you really have to think about. Basically, as I say, try to simulate the challenges that you might encounter when you really use machine learning. So, and as I said, a lot of the things, there are many issues. You'll see even more of it in the next problem set that we're working on now. There are many things you can learn about machine learning algorithms and machine learning in general by playing with things that just listing them as bullets on slides is not going to do it. So hopefully we've accomplished some of it. We definitely want to hear feedback, and I know that in one place we didn't do a good job, and this is with respect to the t-test, that even though it's really a trivial part of the problem set, you may not thought that it's a trivial part of the problem set, and therefore some of you got a little bit anxious about it, but it's basically just applying a formula on what you've done. And the important thing is what you've done. But anyhow, so this will not be significant. So homework 2 is out tomorrow, and I really think that you should start working on it early. Again, the net time that you'll spend on it, depending on your understanding of the material and your programming experience, will be anywhere, I think, between 5, max 15 hours. But it's better to spend the hours early than late, because you'll have a chance to come to the recitation, come to the office hours, ask questions, talk to your friends, clarify things. If you do it the night before, sometimes it's too late to ask questions. And one thing that I do want to accomplish in this problem set, even more than homework 1, is machine learning is an experimental field. You're going to run a lot of experiments. You have to be organized. You cannot just sit in front of your terminal and kind of hack things and type and run and so on, because first of all, it's going to take a long time. Second of all, you will not remember what you've done. So it's really important to be organized. A good script can go a long way. If you're organized with your script, put it there, write it, go to sleep. Tomorrow morning, everything is going to be ready. Your report is typed up and you can submit. So really, it's important to do it, and it's really part of the lesson. Before I give you time for questions, recitation. So first of all, we are moving with the recitation twice a week, Tuesday at 6:30, Wednesday at 5:30. I know that there were some problems getting into 3401 Walnut, hopefully solved. And even though we're still trying to move it to Levine, it's not so easy to find large enough room. So what we're going to cover in the recitation this week is basically preparing you to homework 2, sort of talking a little bit in more details about the algorithmic components that will be part of homework 2. I suggest you come. There was a question on recitation here. You wanted to ask a question about the recitation?
Oh, just I'm not able to go to either.
Office hours you can come to? So send email, send message to Piazza. I want to poll how many people cannot make any. How many people here cannot make any of the 2 recitation, Tuesday and Wednesday? 1, 2. That's it, only 2. I don't think we're going to add 1. I'm sorry. So come to office hours. If you cannot make at least 2 of the office hours, let me know. That we can easily move. So it's very difficult to schedule recitations because we need large rooms, and there are no large rooms. So given that almost all of you can make it, I'm going to try to leave it at this time. But everything that we do in the recitation, we're going to log and make available, plus come to the office hours and you'll get it there. Other questions? Yeah.
What is the second homework?
Second homework is about linear learning algorithms, which we're talking about starting today in the next week or 2. You've seen some of it, but you'll see more. I'll talk a little bit more about it as we go. Yeah.
And are there 6 homework assignments total?
There are going to be 5. Yeah. Yes.
Will you give the answer to the homework so that we can know?
Yeah. We're gonna give you solutions and comments on homework 1. And please ask once it's out, which probably tomorrow. Please ask questions if things are still not clear. Yeah.
Was there a simple rule to the badges?
Okay, that's a very good question. How many people have not submitted 3 yet. Okay, in fact, I can give it. So there is. And this is actually something very interesting, and I mentioned it when I talked about the project. I'm just putting these slides because I want to make sure that those of you that have to do a project remember that it's coming up. You have to start thinking about it. So there is a very simple rule. I can write it in, I don't know, 2 lines. Of course, none of you will find it. And this is a problem with the with the type of learning algorithms that we're teaching. There is a learning algorithm that I'm not teaching anymore because it's out of fashion that could find it. We can talk about it if you want in the office hours. You can actually think a little bit about it. Why is it that there is a very simple rule that can get 100%, will generalize 100%, and we don't find it? It's a shortcoming of the algorithms we're using. But you should have been able to get some predictors that behave okay. Probably the best you could have gone without making huge efforts on features and so on would be low 80s. I doubt anyone can get more than that with what we've done. Anyone got more than that? How much did you get?
Without adding features or
with adding features?
on this test data?
Yeah.
No, 0.93.
Oh, wow. Very nice. Yeah.
Yeah, we got, I worked in a group or something, we got 98.
Okay, so I want to see that. That's actually interesting. So hopefully you explain in your report what you did. I mean, so it doesn't matter. I mean, the grade that you'll get is independent. I mean, as long as you got, something that is reasonable, it's fine. I mean, I didn't expect people to get 98, but it's very nice. So did you, do you understand the concept once you got in the 90s? Can you write it down explicitly in a simple way?
Now we just kind of like added a bunch of features and played around with it. And
Okay.
Which ones caused what?
Yeah.
Yeah, I was in this group. Does it have something to do with belts? Like frequency of belts?
The rule that I can write down does not. It doesn't mean that there isn't a rule that has something with vowels. So there isn't, as you probably know already, you know machine learning enough to figure out that there isn't necessarily a unique representation. So it could be that there is another rule that approximates it very, very well and has vowels in the representation. But the really interesting thing that you should keep in mind as kind of the next generation of people that will do machine learning is that nevertheless, even when you get 93 or 98, you don't understand what's happening. You don't understand this concept. And there is. So in real life, sometimes maybe there isn't a short explanation. In most of the NLP problems, for example, there isn't. In most of the vision problem, there isn't. In this case, there is, and nevertheless, you cannot figure it out. So this is something to keep in mind. Other questions? Yeah?
Is the midterm still on March 1st, even though we didn't have any class last week?
Yeah. So I think it's the best time for the midterm in terms of the material. We will not ask you questions about stuff we haven't covered, so don't worry. We will figure out. So the idea is that I wanted to finish most of the, what I call discriminative machine learning before the midterm. I know now that I will not. There'll be 1 or 2 lectures left. But I still prefer to do it before the midterm so that you get spring break rather than you have to prepare for this, or at least it's somewhere above you when you on spring break. So okay, so let's move on. So what have we done last time? Since it's been a long time, we talked about. Okay, the colors are not so nice. We talked about various learning protocols, and within these learning protocols, we talked about conjunctions. Now, I didn't talk about conjunctions because conjunction is specifically important as a function. It's just a good exercise. It's just one family of functions that is simple enough to think about and derive algorithms for. What we show is that, first of all, protocols matter. We talked a little bit about performance of learning algorithms, and we quantified performance of learning algorithm in terms of how many mistakes will you make before you stop making mistakes. And we gave a theoretical algorithm that showed two things. One is that you, at some point, will stop making mistakes, which might be a surprising thing by itself. Two, that you can actually stop making mistakes quite quickly. That is, small number of mistakes, and by small I mean here logarithmic in the size of the hypothesis space. You cannot hope for more than that, but logarithmic is excellent. I mean, as computer scientists, we always want to be logarithmic in whatever complexity parameter we have. So, you know, this is just an example of how impressive logarithmic is. So if you're thinking about, again, conjunctions, there are many conjunctions over n variables if you think about it. The general conjunction, not only monotone conjunction, which I talked about in the last time, there are 3 to the n, large number, but you can make only n mistakes. In fact, a more interesting subfamily of conjunctions is what I call here k conjunctions, where you have n dimensions, but only k of them are really active, which is a very realistic type of set of functions, because often you have a lot of dimensions, a lot of features, but really only a small number of them are important. You don't know which one are important, but the functions really do not depend on huge number of features. So still, the number of conjunctions of size k is exponential in k. It's n to the k. But logarithmically, just k log n. So think about it. It's if you have a million features, instead of being dependent on a million, now you're going to depend on 20. Huge difference. Times k. K could be at 10 or something like this. So this is huge. Okay, so of course, the one question is, can we achieve this bound with a realistic algorithm? And an even more interesting question, I think, is that everything we did with a finite hypothesis class, right? So we had n dimensions. There's a lot of conjunctions over n dimension, but still finite. Realistically, we are going to deal with continuous hypothesis spaces, which means there are infinitely many functions. Can you bound the number of mistakes even when you have infinitely many functions in your space? Which is, if you think about it, seems like a mystery. Why would that be even possible? Okay, so before I get there and show that this is possible, I want to make one comment on representation. We've already made some comments on representations over the class, and we'll make some more because really representations are important. So assume that you want to learn conjunctions or disjunction or any other kind of Boolean function. You could ask yourself the question, do I really want to learn it as a conjunction, or do I want to learn it as some other function? And this also goes to the interpretation question that you asked me and we discussed before. So if you learn something as a conjunction, it's easy to interpret it. But it turns out that it's hard to learn these discrete functions. So I'm quoting here some NP hardness result. I'm not going to prove it. But it's true that learning the minimal conjunction, even though you know it exists, is actually computationally hard. Similar to learning the minimal decision tree is NP hard. In this case, what we are doing, we are going to do a different solution. Rather than learning conjunctions or disjunction or any other discrete Boolean function, we're going to say, you know what, we're going to learn linear decision functions. This is a much, much larger class. We already know that conjunctions could be expressed as linear decision functions. And it turns out that because you are moving to a lot more expressive class of functions, the combinatorial problem of here is data, try to find in this space of functions a function that is consistent or almost consistent with this data, this problem becomes much easier now. You have a huge space, there are probably many functions there that are consistent with this data or almost consistent with the data, and therefore this search problem becomes easier. And that's a general principle that we are going to use all the time in machine learning. And of course, you should say, well, but there are also downsides to moving to a much, much larger space of functions. What is the downside? Generalization. Specifically, what do you want to say? Another word to saying it is overfitting. Right? You probably saw when you learn with your decision trees. What was the most striking thing that you saw with your decision trees? Say when you move to full decision trees to size 8 decision trees. Yeah.
There was no change in test accuracy, not much change in.
But
the training accuracy was, for full unlimited depth,
it was 1. So you can fit whatever you want with the decision trees, but it doesn't help you so much. Typically, it even hurts you. I think in most cases, without doing something special with the 8 depth, you will get actually better results on tests, even though you get much worse result on training than the full decision tree. So there is a trade-off. Moving to a large hypothesis space could hurt you in overfitting. On the other hand, sometimes you have to do it because computationally you cannot deal with it otherwise. Okay, so just to remind ourselves, so we are going to talk about learning these functions, linear decision function, dot products, WT, dot product with X. X is our data. W is going to be the weight vector that we're going to learn, minus theta, which is some bias from the origin. We talked about the fact that it's an expressive class, so I'm not going to get to it. This is what we have. So we have 2 classes, the purple and the red, and I want to be able to find a linear separator, a linear function that separates these 2 classes. So I'm thinking about it this way. This is just a reminder for those of you that forgot their linear algebra in the last 2 weeks. So this is my weight vector W. This line or hyperplane is the set of all points X such that the dot product Wx is 0. Right? If you want to refresh your memory, take a 2-dimensional case and remind yourself that the W is going to be perpendicular to the hyperplane W dot product X equals 0. Now, this is not going to separate this data. I need to shift it away from the origin to WT dot product X is equal to theta. So above this line, I'm going to have W dot product X greater than theta, below less than theta, and that's what I want to be able to learn. Another thing that we talked about that is just a reminder is that for convenience, I don't want to carry the theta with me all the time, and therefore I'm going to add 1 dimension to W and to X, a fictitious dimension. So instead of thinking about X, I'm going to think about X, comma, minus 1. So instead of n dimensions, it's going to be n plus 1 dimensions. And I'm going to put theta as the n plus 1 dimension of W. Right? So this defines my X prime here is just artificially add a constant here. And I'm going to place theta here. So now the dot product X prime, W prime X is the same as Wx minus theta. So basically what I did is artificially I allowed myself to think about things that go through the origin. And at the bottom you see my poor attempt to show that I'm moving from a 2-dimensional problem to a 3-dimensional problem. But hopefully the algebra is clear. Okay, so now that we have that, we can talk about algorithms. And the algorithm that we're going to discuss most of today, and in fact most of next time also, is probably the most important learning algorithm that you learn in this class. And this is the Perceptron learning rule. We're going to talk about the basic one and a lot of, or at least a few variations of it. The reason I think that this is the most important one is that almost everything we're doing in machine learning today is, in fact, variation of Perceptron. And it turns out that even the vanilla one actually works. Works quite well. Works even better if you add a few things. So in some sense, what has happened in machine learning over the last 60, 70 years is figuring out how to tweak Perceptron a little bit to get a good learning algorithm from it. So, by the way, just an issue of convention. Sometimes you will see in the literature that Perceptron is used not as a learning algorithm, but rather as a representation. It's equated with linear threshold function is a perceptron. I'm not going to use it this way. So for me, perceptron is a learning algorithm, not a representation. Okay, so it's an online mistake-driven algorithm that was invented in the 50s, about the same time by Rosenblatt in the US and by a few Russian mathematicians. So basically, Rosenblatt was a neuroscientist. He thought about it from this perspective, and quoting him, he suggested that when a target output value is provided for a single neuron with a fixed input, it can incrementally change weights and learn to produce the output using the perceptron learning rule. So the way he thought about it is this. So you have inputs, x1 up to x6 in this case. You have a neuron that basically sums up these, and you have weights on the wires that link previous neurons to the new one. And then you have a threshold function that says whether you're going to say 1, you're going to fire or not. So that's why it's called a linear threshold unit. So what was the algorithm that he developed? So first of all, we're going to think about our labels from now on as plus and minus 1. And the function is therefore the sign of the dot product wx. By sign, I mean if the dot product is positive, I'm going to say 1. If it's negative, I'm going to say negative 1. We can think about x either as a Boolean vector, n-dimensional Boolean vector, or a real-valued Boolean vector. W will always be real-valued vector. Given a collection of examples, x, y, from 1 to m in this case, this is what I'm going to do. So we're going to initialize w to 0, for example, and I'm going to cycle through all examples, and in very light gray, which I see that you cannot see here, here it says many times, or potentially many times, because typically one run through the data, a finite data set that you have, is not going to be sufficient for the algorithm to converge. I'm going to predict the label of the instance x to be y prime, sign of dot product wx. If I made a mistake, that is, if my prediction y prime is different than the label I got with the example y, I'm going to update the weight vector. Otherwise, I'm not going to update the weight vector. That's why I call it a mistake-driven algorithm. If I did not make a mistake, I'm not changing anything. If I did make a mistake, this is how we update it. So the new w is going to be the old w plus some constant times yx. X is my example. Y can be plus or minus 1. So let's think about r now as 1, so it will not bother us. This is the learning rate. That means that if y is negative, I made a mistake, I thought it's positive, I'm going to subtract x from w. If y is positive, I made a mistake, I thought it's negative, I'm going to add x to w. That's it. So basically, I'm either I'm adding x to the weight vector or subtracting x from the weight vector. That's the algorithm. Okay, so just to get an intuition of how it looks for people that want to think about it geometrically, here is what I have here. So what I have here is a few examples. Red ones are positive example, blue ones are negative examples. This is my random initialization. This is the vector W, and this is the line Wx equals 0, right? So, and this example here is the next example to be classified. So you can see already that I'm going to make a mistake on it because I'm thinking now that this side of the line are going to be positive examples. So I'm computing Wt. This example gives me negative, while it should be positive. So what I'm going to do is I'm going to subtract it. So this is the vector x as a vector. And I'm going to subtract it from W. And I'm going to get now this W. And we can do this again. Now the example, so this is my new W, the example, and this is my new Wx equals 0. My new example to predict is, this one. And again, it's a positive example. You can already see that I'm going to make a mistake on it. And I'm subtracting this vector here from W. I'm going to get this one. And given that this is my new W, it's here. This is my new Wx equals 0. And now you see that I'm not going to make mistakes anymore on this data. So magically, 2 examples, everything works. That's what we get with Perceptron. Okay, so just to put it again there, this is the rule. Any questions? Yeah?
How is X bit?
How?
How is X bit?
I didn't get the question.
Like, how is X bit?
So someone gave me a bunch of examples.
And you just moved through them.
I just moved through them. Yeah. Yeah.
If it's not possible to draw a line through the 2 data sets, does it just go on forever?
Okay. So I'm going to answer it in the next slide. Good question. Before that, I want to say it's always good to think about the case where X is Boolean, 0 ones, and think about what will happen with Perceptron if you have X's that are 0 ones. So you have your W, you're going to add X to it or subtract X to it. If I have X, which is a million dimensional vector, but only 100 of them are on, the rest are 0. It's a Boolean vector. What does that mean to my update rule? I'm going to touch only 100 weights in my update, which means that the update is actually very, very efficient. And you may want to think about a representation, a data structure that anticipates that. So you don't want to keep your million feature vector, but rather you want to represent it in such a way that anticipates that only 100 are going to be active every time or even less, and therefore you don't want to touch all the million every time. So this is actually important because in many, many applications, the input is Boolean. Okay, so one other thing to think about here, again, anticipating the future, now we don't have a lot of semantic to this, is think about the fact that this dot product being greater than 0 is equivalent to this more complex expression being greater than a half. So if you want to think about why this is true, I put here the graph of e to the x, and you'll convince yourself that if this guy is 0, this one is 1, and therefore this fraction is a half. So this is important because this function is called the sigmoid function, and it comes up many times, and we'll give an interpretation for it a little bit later. And in fact, the interpretation is going to be that this really can be thought about as the probability that the label is 1, given the example. So even though we are making prediction and we don't have any notion of probability, really there could be here some notion of probability, and it comes in the form of this function. Okay, so some history that will also answer your question. Rosenblatt, that came up in the 50s with Perceptron, got a really hard time from a lot of people because they didn't think that this makes sense, partly because we didn't have good enough computers for him to show that he actually can learn if given a lot of data. In particular, one of the key criticism was, well, it can learn only linear functions. So to your question, if the function is not linearly separable, and there isn't any hyperplane that separates purple from red, what can you do then? And this was the key criticism in a book by Minsky and Tappert in '69, a very influential book that I actually highly recommend to still look at it. It's a very interesting book. In fact, there is an edition that came out at the time I was a graduate student, so sort of early 90s, with handwritten comments of Minsky on the original book. So you can buy the book and you'll see his handwritten comments. What they said is, it's not interesting because you cannot express a lot of things. For example, you cannot express parity function like XOR. There are some concept in vision that you cannot express with linear function, and therefore forget it. This was the basis, still is the basis for neural networks. And therefore, because this book was influential, research on neural networks stopped for about 20 years at that time. In the late 80s, came back again, disappeared again after about 10 years for other reasons. And as you read in the news, it's up back again for the third cycle. But anyhow, this was actually very important, even though Rosenblatt actually knew that. He writes in his, when he presents the Perceptron, he says something like to the fact that he knows that it's only linearly separable, but the key question in machine learning, he thought, or in pattern recognition, which was the way it was called then, is what pattern recognition problems can be transformed so as to become linearly separable. So what he had in mind is this transformation that we talked about a couple of times already, where you take data that isn't linearly separable. You need this really kind of ugly curve on the left to separate the data, but you transform the data somehow to something that has more expressive features, but is, over these new features, linearly separable. And this is true. This is still one of the most fundamental problems in machine learning, and we're going to talk a lot about it more. But basically, the way he left it is with two claims. One of them was the convergence theorem. If there exists a set of weights that are consistent with the data, that is, the data is linearly separable, the perceptron learning algorithm will converge. He did not know how long it's going to take to converge, even though at that time people knew. And what he called the perceptron cycling theorem that says that if the data is not linearly separable, which answers your questions, I think, the perceptron learning algorithm will eventually repeat the same set of weights and therefore enter an infinite loop. That actually is a correct statement, but it's not so relevant because it could still do well on the data because we ended up with some linear function. Maybe this linear function is going to do well on the data despite the fact that the data isn't linearly separable and we never stop making mistakes. Okay, so, and the answer is yes, this is what's going to happen. It's going to be pretty robust. Okay, so I'm just rewriting Perceptron for you. And the reason I'm writing it again is because here I'm writing it in the n-dimensional space and I'm separating the W and the theta just to make the point that I don't want you to forget that we are actually learning both W and theta. Okay, so here I'm just writing the update rule separately for W and separately for theta. You'll see sometimes in the literature this way, and sometimes you'll see it after the transformation. Yes?
Is that for every xj and x supposed to be?
X supposed to be the collection of all examples that we have.
Is it looping under for every training epoch? Like, should it be indented, or is that just a separate loop?
No. For every example in X, predict y hat is the sign of the dot product wx minus theta. That's the prediction. If you made a mistake, if y hat is different than yj, update. By update, I mean change w, change theta, and keep on going.
Right, but does that loop happen once for every training epoch? It just
It's for every training example. This is a training example.
is nested. Okay.
Oh, it is nested. It's not clear that it's nested? Okay. So for each example, do this. Okay? Okay, so what do we know? So it turns out that there is a mistake-bound theorem for Perceptron, which is extremely interesting. Okay, so let's talk about this. So what do we know about Perceptron? So Perceptron maintains a weight vector. I'm going to start W in Rn. I'm going to initialize it with W0, which is the zero vector. Once I get an example X in Rn, I'm going to predict according to W dot product with X greater than 0 or not. And this is the theorem that we have about the mistake bound. So given a collection of examples indexed here by T, a sequence of labeled example with xi in Rn, the size of xi, this is norm L2. If you don't remember what it is, this is basically the sum of squares of the coordinated, the coordinates of x, square root of that. The size of x is less than r, capital R. Yi is the label that is -1 + 1. So these are the assumptions that we have. So before I get to the statement of the theorem, I made already one assumption. I made the assumption that the size of all the examples xi is bounded by r, capital R. Is this a big assumption? What kind of an assumption is it?
You are bounding the space or becoming a bounded space, not infinite.
Right, so the x's are within a ball, if you want, of radius r. But is this a big assumption that I'm making? I'm writing down this, but...
No, because you can always take the largest x and
I have a finite set of examples, so of course this R exists. I'm just calling it a name, right? I'm going to take the maximum example and I'm going to call it R. So it's always there, so it's just a notational thing. So I don't really make an additional assumption. Let U, so I'm still reading the next to last line in this statement. Let U, a vector in Rn, and gamma, a positive, is going to be a small positive number, such that, 1, I'm assuming that the size of U is 1, and I'm also assuming that this happens. The dot product U with X, xi, the example xi, times yi, which is the label, is greater than gamma for all I. So all the examples satisfy this. So what does that mean? What do I say here? So first of all, let's just read it. So yi can be plus or minus 1. So for positive example, I'm assuming that the dot product uxi is greater than gamma. For negative examples, I'm assuming that minus this dot product is less than gamma, or that this dot product is less than minus gamma. Okay? Same thing. So that's what I'm assuming. Now let's see if this, what kind of an assumption is this? So I want to say that the data is linearly separable. Right? So there is a hyperplane that puts the purple points below the line and the red points above the line. The way I'm writing it is I'm assuming that there is this gamma such that this dot product times yi is greater than gamma. Is this a big assumption? Yeah?
I think it's equivalent to like assuming that you have like a perfect linear separator in U, right? Like U is just something that gets every example right.
Why is that the same?
Because, well, like you said, the yi's are either plus or minus 1. So, like, if it's minus 1 and you predict right, then that means u dot x is also minus 1, so you get a positive number, which is what that says. And if yi is positive 1, then if you predict a positive number, their product's also going to be positive. So, the only time it's negative is if either your dot product is negative and a yi is positive, which means you were wrong, or the dot product is negative and y is positive.
Right. So basically, I'm going to say this again because this is a notation that we're going to carry with us for a long time, and it's important that you'll understand. Essentially, this says it's linearly separable. If it's a positive example, then yi is positive and the dot product is positive, so their product is positive. If it's a negative example, yi is negative and the dot product is negative, so their product is positive. So you would expect that if I say the data is linearly separable, means that this is always positive. That you would agree with immediately. Why is it okay that I say greater than gamma, some positive number? Do I add another assumption? Or can I always say that? Yeah?
What happened to your shift by data?
Okay. Let's answer this first. So are you asking in response to my question, is it okay?
Well, so we assume gamma is really small, right? Close to the origin?
So I'm working here under the condition that this u go through the origin, because I already did this transformation to the n+1 dimension. Okay, so there exists a linear function that goes through the origin. But still, I'm not saying that the dot product is positive, but rather I'm saying that it's greater than gamma. Should this bother you?
No, because you have a finite set of examples, so one of them's going to be
Right, so it's exactly the same issue that we say with respect to this capital R. I have a finite set of examples, so let's call gamma the distance, the shortest distance that I have among all these examples. So I always, this is always true. If the data is linearly separable, this positive gamma exists. Now, in some sense, you want to think about gamma as your complexity parameters. If gamma is big, it means that all the data points are pretty far away from this u. If gamma is small, it means that at least some of the data points are pretty close to u. So it's some kind of a complexity parameter that tells you how difficult is your data set. And indeed, the theorem says that the perceptron is going to make at most r square over gamma square mistakes on this example sequence. So what does that mean? The r square doesn't matter here. As I said, it's just kind of an indication of the size of the examples. But it says that the number of mistakes we're making is inversely proportional to gamma square, which should make sense to you. Because as we said, if gamma is large, it means that the problem is easy, right? The positive points and the negative points are farther away from the linear separator. And therefore, you're not going to make a lot of mistakes. Pretty quickly, you're going to find some U that makes it. If, on the other hand, gamma is tiny, it's going to take you a lot of tries to fit this linear separator there, and you're going to make a lot of mistakes. So two things here. One is, magically, we're going to stop making mistakes, even though it's an infinite space. Two, we know exactly how many mistakes we're going to make, or at least we know how to bound it, and the bound is relative to a sensible complexity parameter, which is the gap between the positive and the negative examples. Now, it's important, so there is a proof. I'm not going to go through the proof, even though it's beautiful. It's a one-slide proof. You can go over it yourself or ask questions later. I'm explaining it here. It has 2 steps. If you want to go over it yourself, this is the first step. This is the second step, and then we put this together here. You can read it. The most important thing for me now is the following. First of all, the bound doesn't depend on the dimensionality. Doesn't matter how many dimensions the examples have. It doesn't also depend on the number of examples, right? It really depends only on the inherent difficulty of the data set in terms of how far positive and negatives are from each other. This notion is something that is called the margin, and you'll hear about it later. It was popularized into the machine learning community when SVM was introduced in the 80s, but really, as you can see, it was known in the 50s. So that's one. The other important thing to notice here that for us now, weight vectors, W's, and example X's are living in the same space, right? We add W to X, and we think about them as living in the same place. That's important to conceptualize. And finally, what does this theorem mean? It doesn't mean that Perceptron never makes mistakes, or that Perceptron stops making mistakes in general. It basically means if the data has these properties, that is, if the data is linearly separable, you give me 100 examples or 1,000 examples, doesn't matter. I learn and I stop making mistakes on this. What will happen in the future? If the data that you'll show me in the future satisfies the same conditions, that is, it's linearly separable with this margin, I don't care. I will never make more mistakes. So there are conditions, these separability conditions, but with this condition satisfied, everything is going to be fine. Questions? Yeah.
Does the learning rate have a role on this?
No, actually, very good question. So in terms of the bound, it doesn't matter.
What if it's a really small learning rate? You have to iterate.
So here we have to distinguish between theory and practice. In practice, yes. If you, for example, make a mistake and take a tiny, tiny learning rate, you're going to make smaller steps, and perhaps you're going to make more mistakes on the way. But this one is for learning rate 1. The proof is for that. And maybe you'll make a lot less mistakes, realistically, than this bound. This is a theorem that makes an assumption. In practice, what you know is that you'll stop making mistakes, but this could be a very, very loose upper bound. You can do better. Okay, so that's, yes?
Is gamma always the shortest distance between a sample and the hyperplane?
So I define gamma to be this. We're going to talk about margin a little bit more. This is my definition for gamma. It's the small number such that the dot product is greater than it, which is, we can call it the functional margin. We didn't do normalization or anything here. We'll talk about this. Okay, so now the next question that you would ask is probably, okay, what about noise? And one of the magical things about these algorithms, not only Perceptron, sort of a family of algorithms around Perceptron, is that actually they're pretty good. They can tolerate noise. You'll see it in your homework. So Perceptron is going to be one of the algorithms you'll play with. There will be noise in the data. And magically, it actually works quite well. So this can be quantified, and I'm going to quantify it here for two reasons. One, because it's cool that you can quantify it. Two, because the quantities that we're going to use on the way to quantifying it are really important. So here's how I'm going to quantify it. So in the case of non-separable case, what does it mean? It means that I have this U from before. I have this hypothetical gamma away lines. But rather than all the red points gamma away and all the purple points gamma away on the other side, some of the points penetrate into this zone or maybe even go to the other side. It's not linearly separable. So I want first to quantify how non-separable the data is, and this is how we're going to quantify it. So we're going to define this psi I, which is going to tell me how much the example I deviates for my margin. And here is how it goes. So it's the maximum between 0 and gamma minus this guy that you've seen before, yi w2xi. So what does that mean? Let's think a little bit about this. So if everything is fine and the data is linearly separable, what do you know about yi times the dot product wx? It's less than gamma, right? It's greater than gamma. If it's greater than gamma, then gamma minus it is negative, so the max is 0. So if everything is fine, it's linearly separable, this slack parameter is always 0, right? Now, if it moves to within this region, then gamma minus this yi dot product is going to be a positive number, and therefore the max is going to be this positive number. So this slack parameter is going to be positive. And as the dot product grows, this number is going to grow. And it's going to grow linearly with this dot product wx, right? So that's an important, what we're going to call soon, loss function. It really quantifies how much are we losing as we are making mistakes, as we are not within the margins. And how much are we losing? We are losing something that grows linearly with this dot product wx. Before I show you the picture, this was for one example. I want to quantify it for my whole data set. So I'm going to denote D2, the sum of the squares of all these slack parameters, square root, which is, think about for all the examples. For each one I have some numbers, so I write them all in one vector, and this is the size of this vector if you want, the size of the slack vector. And the theorem that I'm not going to prove says that the perceptron is guaranteed to make no more than these many mistakes on any sequence that satisfies what we're saying. And again, I'm bounding the size of the x's in some r, which is always possible. So basically, what does that mean? Before we had r divided by gamma all square, now I have r plus d divided by gamma all square. So essentially, I added the slack parameter, which must be at least sensible, right? So again, I'm inversely proportional to gamma, which makes sense. And the number of mistakes is going to grow as a function of d because, well, if I'm deviating from this gamma region, I have to pay for it. I'm going to make more mistakes. Okay, so again, I'm not going to prove this. I'm going to point a pointer to a paper that has this and has a few other interesting theorems that will, an algorithm that we're going to get to, variations of perceptron, just for the people that are curious about it. The important lesson for me here is that perceptron is actually expected to have some robustness to noise, which is an important, important issue. Questions? Yeah.
If there's noise, but it happens to be linearly separable, would it overfit?
But what do you mean by noise and it's linearly separable? Let's make it explicit.
Well, so if you had a data set that would be linearly separable, but then randomness was added that changes, so random noise was added, but it just so happens that when the noise is added, it's still linearly separable in some way, would that be considered overfitting, or because it's a linear separator, would it no longer?
So really it depends on the type of noise that you add. If your noise results in two examples, or the same example appearing in my data set twice with two different labels, I'm not going to be consistent with it because I'm going to say either positive or negative. But if your noise only resulted with changing the features, so you're saying I'm not changing the labels because I'm still linearly separable. I didn't take a purple point and make it a red and vice versa. All I did was I did what is called attribute noise or feature noise, right? So I had 1,000 features and feature number 2 says 1 and mistakenly I measured it to be 0. If it doesn't matter to the label, who cares? I'm going to learn from it. So as long as the noise is not really changing anything significant, no one cares. Once it does, you cannot separate because you took a purple point and put it on the other side. But all I'm saying, you're going to do quite well regardless of that. Okay, so one comment or two comments here. So it's useful to think about perceptron for Boolean functions. One, because it's simple. Two, because it's realistic. As I said, many domains, your examples are going to be Boolean or categorical, which means a small set of values in each feature, which you can also think about, always think about it as Boolean if you really wanted, with a small blowout in the feature size, in the feature space size. So, for example, I'm not going to give you these answers, but it's useful to think, if I do have a Boolean X, and I want to think about conjunctions, how many mistakes will it make? It turns out, and it's not difficult to see, that perceptron will make a number of mistakes that is linear in the dimensionality. You want to think about here, n is the dimensionality. Where is it coming from? Before I told you, well, it's not a function of the dimensionality, it's a function of this gamma. How come it's suddenly a function of the dimensionality? So this is a puzzle, think about it. Hint, it's a conjunction. So this could, you could think about it. Now, recall that when we talked about halving about 2 weeks ago, we said that there exists a theoretical algorithm that can do this logarithmically in the dimension, k log n. But perceptron, I say, is going to do n. So perceptron, in this sense, is not the best algorithm. There is another algorithm that is called Winnow that was developed much later than perceptron that actually can do it really magical algorithm, as simple as Perceptron, that can learn, for example, conjunctions, and more generally, linear functions. And in the case of conjunction, it's going to do k log n. So if you have a dimension, a conjunction with 1 million features, and only 20 of them are important, it's going to take, rather than about 1 million mistakes, it's going to take 20, which is log 1 million, times 20, which is my k examples, very small number. So you will play with it in your problem set. This is going to be one of the algorithms you'll play with. Okay, so let's move to talk a little bit about some practical issues and extensions. So there are many extensions that we can talk about. Some are necessary for the algorithm to perform really well. I'm going to get to it. These fall into a class of what I call regularization. And we'll talk about. Some are just convenience. I already mentioned that one can convert the output of Perceptron and any other linear algorithm to probability. I didn't explain why this is a probability, but it can become a probability. You basically take this logistic function that I talked about before, 1 over 1 plus e to the dot product, and put a small constant here and change the constant, tune the constant so that the prediction becomes a probability. I'm not going to talk about details of how to do this, but in fact there is a slide here that explains it that I skipped. I want to talk about perhaps the most important extension of Perceptron, which I call average Perceptron. Before I start, there is a misconception about average Perceptron, and some of the literature and some of the packages, including scikit-learn, do not implement it correctly. They just think that average Perceptron is you take perceptrons and you average them. It's wrong. In fact, this version of average Perceptron is a very powerful algorithm with theoretical guarantees that is competitive with all the best linear algorithms out there. But it's a very simple algorithm. So before we get to the algorithm, why do we want to change Perceptron? One reason you may want to change it is because mistake bound is not satisfactory enough. So I proved to you that Perceptron is going to stop making mistakes at some point. But when? In many practical situations, you want to be able to say, okay, I've learned for some time. Now, give me an example. I want to know what is the probability of me making a mistake on this next example. If the algorithm is a mistake-bound algorithm, you don't know. You know that if it's linearly separable and you've already made all the mistakes by the theory, you will not make a mistake. But this is not so realistic. What you really want to know is you want to know, okay, I ran a little bit. What's the probability that on my next example, I'm going to make a mistake? So the question is, can we convert a mistake-bound algorithm to something that has more global guarantees? This is called in the learning literature PAC guarantees. PAC stands for probably approximately correct. We're going to talk about it next week. But this is going to give you guarantees. So the question is, can I convert it? So one intuition to take home before I get to the algorithm itself is, let's assume you ran your Perceptron. You ran it, after 100 examples, it made a mistake, you corrected, updated the hypothesis, you ran a few more, after 10 examples, made a mistake, you corrected, and so on. And then you had a stretch of a size 1,000, and you made no mistakes. Now it made a mistake, you corrected it, you ran after 3 examples, 3 more examples, made a mistake, done. You don't want to run anymore. Which hypothesis will you use and give to your friend to use in the future? Right? In the sequence of learning that I described, there were several hypotheses. Which of those, remember, so I ran 100 examples with the hypothesis, changed it. Ran 10, changed it. Ran 1,000, changed it. Ran 3, changed it. Done. Which of those would you give your friend and say, use this hypothesis? It's good. The last one? So naturally, we always think about it. Okay, we're going to learn until we're done, take the last hypothesis and use it. Is that what you're going to do here? Suggestions? Yeah?
Would that be kind of overfitting, or an example?
Why? So just tell me which hypothesis first, yes?
So in the last round of learning, we only added 3 examples and then changed the hypothesis based on that. So in that regard, it might be overfitting to change the hypothesis after 3, but thinking about it in another way, that's just the 1,113th example and would have changed anyway.
Okay, so I don't want to use the term overfitting here. Yes?
You probably use the one that gave you the 1,000 correct in a row.
Why?
Because you saw that it got 1,000 correct in a row, so that's pretty good. And you wouldn't want to use the last one just because even though you have seen more data, you don't know how your perceptron would perform. You don't know how that algorithm would perform. You have no basis to test it on. But if you use the algorithm that gave you 1,000 correct in a row, it's oh well, I can see that out of the next 1,000 whatever 3 or 13 examples, it got a lot of them right.
So the basic principle we have in learning is that we sample from the population, and we expect that what we sampled from the population during training is about the same distribution as what we're going to experience in test. So the last hypothesis, all I know about it is that it survived 3 examples from my population. Right? I sampled 3 examples, it did well on them. On the 3rd one, it made a mistake. On the previous to last, what I know is that it survived 1,000 examples from my population. It was pretty good. It's by far better than the one that survives 3. Right? So your goal really is to have a hypothesis that is consistent with as much of your data as possible, under the assumption that you sample independently from your data, which we always assume. So basically the idea is that being consistent with more examples is better. And I want to use this idea as a way to improve perceptron. So as a way to convert a given mistake-bound algorithm, specifically perceptron, to something that will give me global guarantees. So the idea is that I'm going to wait for long stretches with no mistakes. There must be one. Think a little bit about it. Because it's a mistake-driven algorithm, there must be a long stretch with no mistakes. Otherwise, you're going to make a mistake. And one of the mistakes in the mistake bound disappeared. Keep on going. Eventually, you will get to a long stretch without mistakes. So, and I'm going to use this hypothesis at the end of the stretch as the one with guaranteed. So average perceptron is an algorithm that exploits this principle in a principal way and returns a weighted average of a number of earlier hypotheses where the weight is the length of the stretch. So if I have 17 hypotheses in the course of my life, I'm going to weigh higher those that survived the longer. So basically, that's the algorithm. There are some indices. So I have m examples. K is going to be my number of mistakes, which is also going to be the number of hypotheses that I'm going to carry. Ci is going to be my consistency count for the hypothesis Vi. I'm denoting the weight vectors here by V. So the ith hypothesis Vi has consistency count Ci. My input is a collection of labeled examples, M examples. I have T, capital T epochs. And at the end, I'm going to output not just one weight, but rather a list of weighted perceptrons, VI, CI. So the way I'm going to run it is I'm initializing all these K, V, and C to 0. T times I'm going to run over all my examples. I'm going to predict Y prime is the prediction sign of my current hypothesis, VK dot product with XI. If I made a mistake, or if I'm consistent, I'm increasing my consistency count. CK is CK plus 1. If I made a mistake, I'm updating. So now I have a new weight vector, VK plus 1 is VK plus YX, just my standard perceptron update. And I'm initializing my consistency count for VK plus 1 to be 1. And I keep on going this way. So essentially what I'm doing is I'm storing on the side each weight vector. And for each weight vector, I'm also counting how many examples it survived. At the end, when I get to predict, given a list of these weighted perceptrons, VI, CI, given an example, what I'm going to do is I'm going to predict this way. So it's the linear sum of my perceptron prediction times its consistency count. Okay, so it turns out that that's a very, very good learning algorithm, as I said, and you will see it also in the problem set. Now, this is also a principle that can be applied on any linear learning algorithm. So you're going to implement 3 learning algorithms, or in fact, you're going to implement, we're going to give you one and you're going to modify it slightly to implement 2 others, and you'll implement this average perceptron on top of them. One important point that we are making in the homework, and this is going to be my last comment, is that this seems like you need a lot of memory. So, because if you have high dimensionality, and in one of the problems you will have high dimensionality, and you have, I don't know what, 100 or 1,000 different weight vectors, you'll run out of space. So there is a simple trick that you can think about that will prevent you from keeping all the VI, CIs. You will, in fact, manage to do it by keeping only 2. A running average of everything you've seen in the past so far, and the current one. So if you think a little bit, you can figure out a way to do this, and therefore, memory-wise, it's not going to be a problem, and this algorithm is going to do better. Final questions? Yeah.
I'm just thinking about these streaks of no mistakes. Would it be possible to improve the model perhaps by emphasizing the later streaks, even if it's of the same length? Because, I mean, my intuition is that since the later models tend to be more refined, if you make 100 no mistake streak later on, maybe that's an even better model compared to the one.
You'll have to make assumptions in order to justify what you're saying. Under the independence assumption of the examples, you cannot argue that. But maybe under some conditions, your intuition actually holds. Okay, so we'll continue from this point on Thursday. And as I said, tomorrow you're going to have homework 2 out.